All right, so this is our first live stream because last unit we didn't get to do one. So welcome to your first live stream. Here's the deal with this. If you're in my class, you guys can message me at any time on Remind, or you can use the chat box on YouTube. You just have to be logged into your account. So some people are talking about my sweatshirt over there right now. You can probably see it. If you are not in my class, then you right down below me to sign up for a Remind link, and you can just send me questions at any time. Doesn't matter when, just send them to me whenever you have them. I am a couple seconds ahead of you guys because there's a slight lag with live streams. So if you have a question, just send it. I will get to it as soon as I can. We are going to go through like the major topics, but if there are things I don't go over or you have questions about, then send them and ask them. And the other thing that I would say is if you're watching this on a replay, use the fact that you're not watching it live to your advantage, right? So the idea that you have fast forward, rewind, pause, all of those things, use those to your advantage, right? Pause it, try it on your own. The blank document for tonight is also up on my OneNote. So if you go under Unit 2, the blank document's up there. So if you want to work along with me or try it on your own independently after, you can do that. So let's get started. So first of all, in your unit overview packet, in your organizer, this is the list of learning targets that you have for this unit. Don't forget that you guys have this, right? This is a list of everything you should be able to do. So you can say, I can explain this, I can do that, I can find average rate of change, and use these as a study guide and go through and check them off as you do them. So that I just want you to keep in mind you have. But we're going to sort of start with what are the rules that you're expected to know, have memorized, and then we're going to do tons of examples. That's our big plan for tonight. So as far as rules, for derivative rules, you've got to know the basics. You've got to know power, product, quotient, chain. And then for actual derivatives of functions, you need memorized all of your trig functions. So sine, cos, tan, secant, cotangent, cosecant. You should know e to the x. You should know ln x. You should know a to the x. And you should know log base a of x. As far as inverse trig derivatives, there's two big ones that you make sure you need to have memorized. And that would be arcsine and arctan, which is right here. Those are the two big ones that come up the most on AB exams. The way that I tell these apart and the best way to kind of keep them straight is arcsine has the S in it, right? Sine inverse starts with an S. That's the one with the square root and the subtraction. And arctan has the T. That's the one with the plus, right? That looks like a T. So that's how I keep those straight in my head. The other thing I would remember about your derivative rules, any trig derivative, if the function starts with a C, its derivative will be negative, right? And cofunctions are very similar to each other. So sine and cosine are sort of cos and negative sine. Tan and cotan, secant squared, negative cosecant squared. Secant and cosecant, again, are related. So keep that in the back of your mind. As far as other things, implicit differentiation, remember that this is just an application of the chain rule. So you're taking the derivative of y with respect to x. And so we think about an inside and an outside, and we'll do some practice on those. And then derivatives of inverses. And the big thing you need to remember with that is derivatives of inverses are reciprocals at corresponding points. So that's sort of like your rule sheet of things you need to make sure you have memorized. And what we're going to spend all of the rest of our night doing is applying those rules. So let's start with talking about average versus instantaneous rate of change. Average rate of change is something you've talked about since 8th grade. You've talked about it being the slope, right? In physics, you talked about average velocity. But instantaneous is really a concept that depends on calculus, right? That idea that we can take an infinitely small interval and look at the rate of change over it. So let's look at this first one. S of t is measured in feet traveled in t minutes. Find the average rate of change between 0 and 4, and then interpret in context. So this is really just asking me to do s of 4 minus s of 0 all over 4 minus 0. And we can plug in to get those values, right? So my denominator is just going to be 4. S of 0, I can plug that in pretty easily, is 3. S of 4, if I plug into that, that would be 32 minus 20 plus 3. So that's what? 12 plus 3, so 15. So this comes out to be 12 over 4, which is 3. Now thinking about your units there, anytime you do slope, you're doing change in y over change in x. And so change in y here is in feet. Change in x, or change in t in this case, is in minutes. So 3 feet per minute. So if I was going to describe this in context, I would say, okay, so on average or approximately, we need to say that, right? So on average, and then I want to remember to tuck in my answer, right? So I need time, I need units, and I need context. That's sort of what I'm going for in here. So on average, the position, right, or whatever we're talking about, the object, let's call it the object, is moving, so there's my context, at a rate of 3 feet per minute. That's my units. And now I just need the time from t equals 0 to t equals 4 minutes. And obviously you will write neater than me because you are writing on actual paper and on iPad. Okay, so let's talk about instantaneous. Average rate of change is just your slope, but instantaneous is where we need to get a little bit more technical. There's 2 different ways you can deal with instantaneous rate of change. So both of those are the derivative. The first limit definition of the derivative you need to know is the limit definition of a point. So this is f prime at a particular c value. So this is going to be the slope here, right? F of x minus f of c over x minus c, and then take the limit as x approaches c. So if I think about my interval, if this is x and this is c, I'm taking the limit as x gets closer and closer to c, as that interval becomes infinitely small, right? The other way that we can figure this out is to find the general derivative and then plug in a value. So the general limit definition is this one, that's the one with the h. And so this is the one where we have a graph and we've got like x, and then this distance is h, and so that's x plus h, and we're looking as h approaches 0, as those get infinitely close, right? So let's look at how they might ask this. There's 2 different ways you'll usually see this, graphically or algebraically, and within that there's different ways they can ask. So let f be given by the graph at right. For what values of c does the limit as f of x, or as x approaches c, of f of x minus f of c all over x minus c equals 0. So when I look at this, the first thing that I notice is that this jumps out to me as looking like a slope, right? And so when it looks like a slope, I'm going to say, okay, that's probably a derivative. I see that it is because it's the slope as the distance gets infinitely small. So this is the limit definition of the derivative. So what's really asking me is, where will f prime equal 0, right? It's saying at what value of c will f prime equal 0. And so I'm looking for a time where my slope of my tangent line is 0. So looking at this graph, really I'm looking for one of those turning points, or at least a flat point. So here I've got a horizontal tangent, here and here. So there are 3 different values where we have a tangent line with a slope of 0, and that would be at negative 1.5, at 2, and at 4. And you'll always be able to tell on a test exactly where those points are. You're not going to need to estimate it. So just make sure that you check for where those are. Okay, let's move on. Let's talk about some algebra. So algebraically, there's sort of 2 different ways they can do it. The first way is they can give you a limit definition and then ask you what it equals, right? The second way is to ask you to actually calculate the limit definition. So let's start with sort of the easier scenario, just identifying that structure. And then from there, we can talk about actually calculating it. So first one, when I see this, now you could look at this, try to sub in for the limit, and realize that you get 0 over 0. And you could actually do this as just a L'Hopital's problem. But we're not going to do that because I recognize that this is actually a limit definition of the derivative. So remember that we said this would be f of x plus h minus f of x all over h, and it would be the limit as h approaches 0. I see that structure here. So what I see is that this would be f of x plus h. So f of x plus h, what I'm thinking is that is going to be x plus h, where maybe my x got replaced with an 8, right? So think about what that would make your f of x. That would make f of x equal to the cubed root of just x. And think about if that makes sense. So this should be f of x plus h, then this should be f of that x value. Well, if you actually do the cube root of 8, that's what that is, right? So what I'm looking at is that this is the limit definition of the derivative where f of x is the cubed root of x and where your x value equals 8. And so if it's asking you what that equals, instead of taking the limit, which again, you could just do with L'Hopital's rule, but you could also just find f prime, which would be 1/3 x to the negative 2/3. And then you could plug in 8. So you could say, okay, well, f prime of 8 would be 1/3 times 8 to the negative 2/3. And think about what that means. 1/3 times 1 over the cube root of 8 squared, right? So that would be 1/3 times 1/4. And so that would give you a 1/12. Now again, you could still do the limit, but if you recognize that it's a derivative, this is a lot faster than having to go through and do the derivative of the top, derivative of the bottom, and prove that L'Hopital's applies. Okay. This should be plugged in. Oh, I unplugged it. Hang on. Okay, we're back. All right, so let's look at the next one. So limit as h approaches 0 of sine 2x plus h minus sine 2x all over h. This looks much more like a true limit definition of the derivative, because in this one you can see x plus h in there, and in this one you see that it's just an x. So it's a little bit easier for me to identify this function. This function, remember this is f of x plus h, which means this is just f of x. So my function here is sine 2x. And it's asking me to find the derivative. Now again, could you try to do L'Hopital's on this? Sure, but I would not. I would say I recognize that this is a derivative, and so I'm going to take the derivative of that. So f prime of x is going to be the cosine of 2x, because this is a chain rule. Take the derivative of the outside, leave the inside alone, times 2, because that's a derivative of the inside. So this would be c 2 cos 2x. Okay, let's keep going. Let's actually do a limit definition by hand. So use the limit definition of the derivative to find the derivative of y equals x minus 2 over x minus 1. Then use your answer to write the equation of the tangent and normal lines at at x equals 3. So let's start with that. If I want the limit definition of the derivative, I'm going to be doing the limit as h approaches 0 of x plus h minus 2 over x plus h minus 1 minus x minus 2 over x minus 1 all over h. So again, I did f of x plus h minus f of x all over h. So from there, now I need to do some algebra on this. If I sub in, I wind up getting 0 over 0 indeterminate form. So I'm going to start doing some algebra. So I'm going to multiply through by my LCD, which here would be x minus 1 times x plus h minus 1. And same thing in the denominator. So this gives me limit as h approaches 0. In the denominator, I like to leave things in factored form because my goal is for some of those things to cancel out. So that's going to stay in factored form. In my numerator, I'm going to distribute out what I can. So here, the x plus h minus 1 will cancel. So I just have x plus h minus 2 times x minus 1. Here, the x minus 1 will cancel. So I've got x minus 2 times x plus h minus 1. And there, if you try to sub in, you're going to wind up with 0 over 0, right? So we wind up with an indeterminate form. So let's do some simplifying. So in the numerator, let's actually multiply these out. I'm going to leave my denominator alone. So in the numerator, I'm going to actually multiply out what I can. So this is going to be x squared minus x, and then plus xh minus h, and then minus 2x plus 2. So that's that first one multiplied, right? Minus, now let's look at these second ones, and I'm going to keep this in parentheses for a second. This is going to be x squared, xh, minus x, and then minus 2x, this is getting long now, minus 2h plus 2. So that's at least multiplied all the way out, right? Let's see what we can simplify. So I'm going to distribute my negative out to everything. So doing that, this becomes minus, this becomes minus, this becomes plus, 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 and minus. So I'm getting rid of those parentheses by distributing out my negative, right? And then we can start simplifying from there. So in my numerator, the x squareds will cancel. I've got a minus x and a plus x. I've got a minus xh and a plus xh. I have, let's see, what else do I have? Minus 2x and plus 2x. And then I've got, let's see, plus 2 and minus 2. So what I wind up with here is just negative h plus 2h, right? So that's h in my numerator over h times x minus 1 times x plus h minus 1. Limit as h approaches 0 of that, right? So now from there, what I can do is I can simplify the h's, and then you could actually take that limit, and that would give you your derivative. From there, you could plug in to get your derivative and then come up with tangent and normal lines. Okay, if you have questions, send them to me, but I think limit definition has been something that we're pretty strong at, and I don't want to spend like ages and ages on something we're doing pretty well with. All right, let's look at differentiability. So the big idea with differentiability is that the slope of the tangent from the left has to equal the slope of the tangent from the right. And so that's something that we're looking about. Being differentiable implies that things are continuous, but being continuous does not imply that things are differentiable. So if I look at these, let's say I'm looking at like x equals 1 here. If I look at my tangent line from the left and from the right, those slopes look the same. That is differentiable. Notice it's continuous and it has a consistent slope at that point. If I look at number 2, this is not continuous, and the big idea here is there would be no tangent line because like the tangent to the point would be up here. It's not even defined there, so that one is not differentiable. It has to be continuous to be differentiable. For the next one, my derivative from the left and my derivative from the right, like they wind up being different. This has a corner or a cusp, right? And so that would not be differentiable because of the cusp. This one is not differentiable because it's not continuous. And this one is not differentiable again because of that corner. We've got different slopes from the left and from the right. So that cannot happen here. So if I want to show that something is differentiable, I need to first look that it's continuous at that point. And second, show that the limit of the derivative from each side is the same. So those two criteria need to be true. So let's say that I look at this one. So show that the following is differentiable at x equals 1. If it's not, explain why. So looking at this, I have f of x, and let's try showing it's continuous. That's the first thing I need to do. So to show it's continuous, I'm going to find, I'm looking at when x equals 1. I'm going to find f of 1, which is going to be absolute value of 1 minus 1, which is 0. And I'm going to take the limit as x approaches 1 of f. And that also happens to be 1 minus 1, which is 0. So I could say, therefore, f is continuous at x equals 1 because the limit as x approaches 1 of f of x equals f of 1. So that's my first criteria, right? That whole idea that this needs to be continuous to be differentiable. From there, we need to show it's differentiable. And so to do that, I need to look at the derivative from both sides. So let's look at this function. I don't know a way to find the derivative of absolute value right now, just off the top of my head, right? So I'm actually going to rewrite this using a piecewise function. So this would equal 0 at 1, right? It's absolute value of x minus 1. If you plug in a number bigger than 1, the absolute value, the expression in there would be positive. If you plug in a number smaller than 1, the value inside would be negative. And so anywhere above 1, this expression will stay the same. Anywhere below 1, this expression will be the opposite. So 1 is going to be my boundary, below and above. And so this is going to be above, it's going to be x minus 1. It should stay the same. Below, it's going to be negative x plus 1. So that's my function, which means that my derivative is going to be negative 1 when x is less than 1 and positive 1 when x is greater than 1. And actually, technically, we could have an equal to on one of those top ones. So looking at this, I'm going to look at my limit as x approaches 1 from the left of f prime. And that means look at my left-hand piece, that's negative 1. And the limit as x approaches 1 from the right of f prime, and that's going to be positive 1. And so I see that those are not equal, so this is not differentiable, or f is not differentiable at x equals 1 because the limit as x approaches 1 of f prime does not exist. And there's other ways to say that. You could say the limit from the left does not equal the limit from the right, but either way, that's just basically saying that that limit does not exist. Okay, there's another differentiability one on here. Feel free to try that on your own, pause the video, but we're going to skip through that because I think differentiability, again, once we review the methodology, you guys were doing pretty well at. All right, let's just do some basic derivatives. My concern here, guys, is the calculus. The algebra comes down to you being able to simplify. I will do some simplifying, but there will be somewhere what I'm going to talk through as the calculus because I want to make sure we're solid on that. So let's look at these. The big thing that I look at when I take derivatives is I look for structure, right? Is it a quotient? Is it a product? Is it a chain? Is it implicit? What's the inside? What's the outside? All of those things become important. So let's look at this first one. I don't see any simplifying that I can do first. If there was any, I'd do it, but I don't see any. So because of that, I'm going to say, okay, what's my structure? My structure here is that this is a quotient, and so I'm going to use the quotient rule here. So f prime would be low d high minus high d low, square the bottom, and away we go. And so that's going to be x secant squared x minus tan x over x squared. Now, there's different simplifications you could do. You could write everything in terms of sine and cos. You could divide each part by x. But again, unless it's like a multiple choice and I know exactly what way I want it simplified, you can work with it in different ways. So I'm going to leave it for there right now. But if you have a question about what you could do, send it to me. Okay, I'm happy to answer questions. You guys are mighty quiet tonight. All right, let's look at this second one. So f of x equals e to the sine x. So that one right there is a chain rule, right? It's a function in a function. And what we need to identify here is that the inside is sine, the outside is e to that power. If it helps you to write u equals sine x, and then this would be e to the u, go ahead and do that. But I'm going to talk through kind of doing it without rewriting it. Either way works for me. So I know it's chain rule. So I'm going to do the derivative of the outer part, which is e to the x, right? Or e to the u. So the derivative of e to a power is e to that power. So the derivative of e to the sine will be e to the sine. But then we need to multiply by the derivative of the inside, which is cos. My biggest concern on something like that is just making sure that you don't write this as e to the x, right? It's e to whatever that power already is, because that power needs to stay the same. It's why we spent so much time rewriting them like this at first, because the derivative of e to the u is e to the u times u prime, and then u prime would be cos there. Okay, next one. Let's look at this. This is a peanut M&M, right? We've got inner, a little bit out, a little bit out. So I'm going to start by rewriting this just because I don't love that 1 over x in there. So log of sine of x to the negative first. So that's how I'm starting. So let's go outside in. Let's talk about chain rule. So f prime would be, okay, so derivative of a log. And remember, whatever the inside is, it's going to stay the same. So derivative of log is 1 over whatever x is. So whatever our inside is. Let me write this up here first. So derivative of log base a of x is 1 over x ln a. So here my base is 10 and x is really this whole thing. So this would be 1 over sine of x to the negative first times ln 10, right? So that's the derivative of log times, now let's go in a layer. So now I've got sine as my next layer. Derivative of sine is cos, leave the inside alone. And then the innermost layer, x to the negative first, is negative x to the negative second. And then simplification, I can't talk on a Sunday night. simplification for that, the only thing I'd really do is maybe bring that x to the negative second down to the bottom. So you could make this x squared and then sine x to the negative first, ln 10. But there's not a whole lot of simplification you can do there. Okay, let's look at one like number 4. So what's calling out to me on number 4 is that this one is not solved explicitly for y. In this, it's implicit in the equation that y could be solved for x. So we assume that that could happen. We assume that y is a function of x, and then we're taking the derivative from there. So let's do this. So we're taking the derivative with respect to x. Derivative of 1 is 0 minus. Now this is a product, so I'm going to need to do product rule here. So the first times the derivative of the second plus the second times the derivative of the first equals 1 minus dy dx. So I wind up, when I distribute this negative s, having negative x dy dx minus y equals 1 minus dy dx. Now I'm going to get all my dy dx's onto the same side. So I am going to add the 1 over from the right side. And I'm going to add the y over to the right side there. Factor out the dy dx. Negative x plus 1 equals 1 plus y over negative x plus 1. And because I'm dividing that over, that would go away. So that is my final derivative. Okay, let's see what else we can look at. So let's look at some where maybe we're taking a derivative, but it's not in like that basic form, okay? So this says g of 2 is 3, g prime of 2 is negative 1. What is the value of g of x over x squared at x equals 2? So let's look for the structure here. I'm taking the derivative, and this structure immediately, I see that that looks like a quotient to me. So let's take a look at how we do that. So I would do low d high, which I don't know what it is, but I know it's g prime, minus high d low, square the bottom, and away we go, right? And it wants this when x is 2. So let's plug in what we know. So this would be, I'm going to come down here. This would be 2 squared times g prime at 2, which is negative 1, minus g of 2, which is 3, times 2 times 2, right? You're plugging in 2 for x, all over 2 to the 4th. There's my expression. That's what I'm going to be simplifying. So from there, now I'm saying, okay, this would be, I'm going to go over here now, negative 4, and then this is 12, minus 12, all over 2 to the 4th, which is 16. So negative 16 over positive 16, so that should come out to be negative 1. Okay, I really, really, really like this next question. This really has you using algebra, and it has you using notation. If you understand this, you understand kind of this whole structure thing pretty well. So for this one, it says y equals x squared times f of x. What is y double prime? So we're going to take the first derivative and then take the derivative of that, right? Get to my second derivative. So let's start with getting the first derivative. I recognize immediately that that product is a structure, or that structure is a product. So y prime, I'm going to use the product rule. So the first times the derivative of the second plus the second times the derivative of the first. That's what I'm starting with, right? X squared f prime plus f times 2x. That's my first derivative. Now, let's try to get the second derivative in here. So now I need to take the derivative of that. And what you're going to notice here is that I now have 2 products, right? So I now have 2 products. So let's start with the first product. So this first one, I would do the first times the derivative of the second, which would be f double prime now, right? The derivative of the derivative, plus the second times the derivative of the first, plus, let's do the same thing for these, the first times the derivative of the second, plus the second times the derivative of the first. And so I wind up with this being my expression for my second derivative. So now from there, let's see what we could simplify. This is the only one with an f double prime, so that's going to have to stay. This one and this one are both 2x f prime x. So that's actually going to be 4x f prime x. And then this is just 2f of x. And so then match up with that. So x squared f double prime, 4x f prime. So it's got to be d or e, and 2f of x. So this should be answer D. Okay, let's look at a little bit more what they can ask you with implicit. And remember, keep sending questions as you have them. It has been such a quiet live stream so far. So on this one, I'm giving you this, x cubed minus xy plus y squared equals 3. Part A says find the derivative. Part B, find all points on the curve whose x-coordinate is 1 and write an equation for the tangent line. Part C, find the x-coordinate of each point on the curve where the tangent line is horizontal. So let's start with A. I want the derivative of this. So I'm going to take the derivative of each part, just like we did before. So x cubed, derivative of that is 3x squared, minus, this is a product, so I'm going to do product rule. The first times the derivative of the second, plus the second times the derivative of the first, plus 2y dy dx, because that's a derivative of y, equals 0. So my right side equals 0. One of the most common mistakes is people telling me that that right side should still equal 3. Okay, so from here, I wind up with 3x squared minus x dy dx minus y plus 2y dy dx equals 0. Now I'm going to move anything that doesn't have a dy dx over to the right side. And on the left side, I'm going to factor out a dy dx. So negative x plus 2y. And then the right side is going to be y minus 3x squared. So just moving that over. And I wind up dividing, so I've got dy dx equals y minus 3x squared over negative x plus 2y. So there's my first derivative. See if you guys have questions about that. I'll give you another second. See if there's anything there that I can answer. Okay, so the second one says find all points on the curve whose x-coordinate is 1 and write an equation for the tangent line at each of these points. So let's start with the points and then we'll worry about the slope. So I know the x-coordinate's 1, but I don't have the y-coordinate. So I'm going to go back to my original equation, plug in x, and get out y. So here, this is going to be 1 minus y plus y equals 3, right? Or y squared, sorry. So I wind up with a quadratic equation. This is actually y squared minus y minus 2 equals 0. Factor that. So I've got y minus 2, y plus 1. And so my y values are at 2 and at negative 1. So we have two different points where this would have an x-coordinate of 1. 1, 2, and 1, negative 1, right? So my x-coordinate's 1, but I have two different coordinates where that can occur. So from there, now I'm going to find my derivative. So I've got my derivative equation. So let's look at 1, 2. So dy dx evaluated at 1, 2 would equal 2 minus 3 over 1 plus 4, negative 1 plus 4. So that becomes negative 1 over 3. So that's your slope there. So your tangent line there is y minus 2 is negative 1/3 x minus 1. Now we do the same thing at 1, negative 1. So if I plug that in, dy dx evaluated at 1, negative 1 would be, let's plug that in. So y is negative 1 minus 3 all over negative 1 minus 2. So that becomes negative 4 over negative 3. So this would be y plus 1 equals 4/3 x minus 1. So there's my tangent lines. Okay, and then the last thing, find the x-coordinate where the tangent line is horizontal. Tangent lines are horizontal when the fraction or when the derivative equals 0, right? So we're looking for where dy dx equals 0. And so in order for that to happen, the numerator of my fraction must equal 0, right? So that is where that occurs. That's going to be anytime y equals 3x squared, right? And then to get those actual x coordinates, you could take this, plug it back into there, and then actually solve for x. I'm not going to do that now again because that's just an algebra problem. But the concept of knowing that you need your derivative to equal 0, and then that's going to be where the numerator of your derivative is 0, that's really what we're looking for there. Okay, keep sending questions if you have them. Next one, the second derivative in terms of x and y, that's what I want. And I'm given the function or the relation. So let's start by taking the first derivative. So first derivative would be 2y dy dx equals 2x plus 2, right? So nothing crazy there, 2y dy dx equals 2x plus 2. So dy dx here is going to be 2x plus 2 all over 2y. And it's always helpful to simplify down if you can, because that's going to make things easier in the long run, x plus 1 over. Now, we need our second derivative. So that right there is a quotient. So to find my second derivative, I'm going to do the quotient rule. So d squared y over dx squared is going to be low d high minus high d low all over low squared, right? Square the bottom and away we go. So that's going to be, in terms of x and y minus x plus 1 times x plus 1 over y all over y squared. Now, I do want to simplify, and what I notice here is that the denominator of that is 1, that is 1. So I'm going to multiply through each part by my common denominator, which is going to be just a y. So here you're going to get y squared minus x plus 1 squared, because the y's there will cancel. And the denominator going to get y cubed. So this is your second derivative in terms of x's and y's. Okay, so we did get a special request to look at the other differentiation one. So we will go back to that in 1 second. I want to do sort of one more. Actually, let's do it now, because we will talk about inverses after this. So here was the other differentiation or differentiability one, and it's going to be the same as what we did here. In order to tell if it's smooth, you need to check and see if your derivative from the left is the same as your derivative from the right. So looking at this one, first let's see if it's continuous. And to do that, I'm going to find, first of all, the value of the function, so y evaluated at x equals 1, which is going to be looking at this part, so that's 0. The limit as x approaches 1 from the left of y, which is going to be this piece, which is 0, and the limit as x approaches 1 from the right of y, which will be looking at this piece, which is 0. So here I could say y is continuous at x equals 1 because limit as x approaches 1 of y equals y evaluated at x equals 1. So that's sort of how I know there that that would be continuous. Now, from there, I want to check and see if it's differentiable. So again, I'm checking to see if my derivative from the left and my derivative from the right are the same. So let's find y prime here. So from the left, your derivative would be 3 times x minus 1 squared, chain rule, right? Times the derivative of the inside, which is 1. And that's going to be whenever x is less than 1. From the right, it would be 2 times x minus 1 to the first times the derivative of the inside, which is 1. And that would be when x is greater than 1. And we don't know what happens at x equals 1 because we don't know if this derivative exists yet. So I'm going to do the limit as x approaches 1 from the left of y prime. And that's going to be 0 again, right? And then the limit as x approaches 1 from the right of y prime, which is still going to be 0. And so what I'm seeing is from the left and from the right, the slope of both of these is approaching 0. So since that happens, I can tell that they will meet smoothly there. So since this is continuous, it's also differentiable. So I could say, therefore, y is differentiable at x equals 1 because the limit as x approaches 1 of y prime exists. So that's how I know it's going to be smooth, because my derivative from the left and my derivative from the right approach each other. If that didn't make sense, keep sending questions, but thank you for asking to go back to that. Okay, so let's look at inverses, and then we're going to talk about L'Hopital's, and then we're done for the night, other than specific questions you guys have. So looking at this one, select values of a monotonic function g of x and its derivative g prime are given. Monotonic tells me that this function is always increasing, and so that's going to be important when I'm talking about inverses, because that means it passes a horizontal line test. So its derivative g, okay, are given. So I want to find g inverse at 1 and g inverse at -3. So let's start with this first one. So I want x, g of x, g prime of x. And then I want x, g inverse of x, and g inverse prime at x. This is what I'm looking for. So I'm going to start kind of there. So it asked me for g inverse prime at -1, which means that -1 is my input for the inverse, right? That's the input for the inverse. If it's the input for the inverse, it means it's the output on the original. So again, any input for the inverse is the output on the original. And now from the table, I can say, okay, well, where does g have that as an output? Oh, I'm sorry, it's +1. There we go. Where does g have that as an output? G has that as an output right here, which is at -1. So if it's my input for g, it's my output for g inverse. Now from there, we can fill in what we've got. So g prime is of -1, we're going to look right here, is -1/5, which means g prime at +1 will be the reciprocal of that, which is -5. Okay. Next one, we're using the same table, so I'm going to erase that, and I'm going to make my table again. So x, g of x, g prime of x, and then x, g inverse of x, and g inverse prime of x. I want g inverse prime at -3, so that's the input to my inverse, which means it's the output to my original. So let's go back to that table and see what we've got. So g equals -3 when x is 4. So I know those will be my respective inputs or outputs. And then from there, g prime at 4 is -2, which means g inverse prime would be -1/2. The biggest mistakes I normally see on those is people think that they're perpendicular. I dropped my iPad. They're not opposite reciprocals. They're just reciprocals, right? They don't have to be perpendicular. So just be careful with that. Okay. Let's look at, we've got like 2 more. This question is my favorite question of all time. This is from the 2007 exam, and I think the average on it was like a 1 out of 9. It's a really hard question, but if you know what you're doing, you're going to nail these. So we've got this function. We've got f prime, g, g prime. F and g are differentiable. The tables give the values for all of the functions and their first derivatives. So f inverse is the inverse of f, right? An equation for the line tangent to f inverse at x equals -1. So let's start with this one. So knowing this, I'm going to make my table. So I have x, f of x, f prime of x. And then x, f inverse of x, f inverse prime of x, right? So that's what I'm starting with, because I know I want the tangent to f inverse at -1. So my input is going to be -1, which means that will be my output on f. So let's look at f. Here's f. That equals -1 when x equals 2. So I know I can swap those values. And then from there, f prime at 2 is 4, which makes f inverse prime 1/4. So that's the derivative, right? But we want the equation of the tangent line. Here's why this table is so helpful. Here's your point, there's your slope. And so now to write that equation, I can just do y minus 2 is 1/4 x plus 1. Boom, there's my equation, done. Okay, the second one, B, says h is f of g of x. So I'm already seeing that that's a chain, right? It's a function in a function. So to find the derivative of that, I'm going to find h prime by doing the derivative of the outside, leave the inside alone, times the derivative of the inside. So there's sort of my formula. Now it wants h of 0, or h of 1, which will be f of g of 1, so no calculus there. And then h prime of 1, which will be f prime of g of 1 times g prime of 1. So let's figure out what we can. For the non-calculus one, let's start with that one. So g of 1 is -1. So I'm just doing f of -1. And f of -1 is 3. So that's h of 1. Now from there, I'm going to do h prime. So f of g of 1, here, g of 1, we said was -1. So this is f prime of -1. And g prime of 1, here's g prime of 1, that's 2. Now f prime of -1 is going to be -2. And so this comes out to be -4. Okay, and then this says, what is h inverse prime of 3, given that h inverse is the inverse of h? So let's see what we know. So x, h of x, h prime of x, and then x, h inverse of x, h inverse prime of x. So let's see what we know. We want h inverse prime at 3, which means our output on our original must have been 3. There is a reason that they had me do this, right? There was no reason for that. H of 1 is 3, right? So h prime of 1 we said it was -4, which means h inverse prime is -1/4. So if you understood that one, guys, that's you really understanding the inverse, like on a deep level, which is awesome. All right, last thing we're going to talk about is L'Hopital's rule. And this is a way to find limits when you wind up getting like an indeterminate form and you don't have to do all the algebra, or you can't do all the algebra. So looking at this first one. So k of t equals t minus 5 over z of t plus 3. Z of t is a differentiable function where z of 5 is -3 and z prime of 5 is 7. Find the value of the limit as x approaches 5 of k of t, or state that it does not exist and justify. So I'm starting out by saying, okay, I'm finding this limit. In my head, I'm direct subbing. If I direct sub in 5, the numerator will be 0, and the denominator will be z of 5, which is -3, plus 3. So it's also 0. So I can already tell this is coming out to be an indeterminate form. So in order to use L'Hopital's, here's what I need to do. I'm going to do the limit as t approaches 5 of the numerator. That is 0. I know that. I did the substitution, right? And then I'm going to do the limit as t approaches 5 of the denominator, which should be z of 5 plus 3, which should be 0. Now, it said to justify, and we have to be careful with this. This one, I just did the direct substitution. That is justification. But this one, they didn't tell me that that limit was equal to z of 5. And so the reason that this is true is because, so I would say the limit as t approaches 5 of z of t equals z of 5 because z is continuous. And as long as we know that, then we can use that value for our limit. Now, once you get 0 over 0, you can say, therefore, L'Hopital's applies. Make sure that you're showing those limits separately. From there, L'Hopital says that that limit that we started with will be the same as if we take the derivative of the numerator, which is 1, over the derivative of the denominator, which is z prime, right? The derivative of the constants are 0. And so now I can take this and I can say that's 1. The limit of the denominator is 7. And then I'm done. Okay, let's look at one more. So let h be the function whose graph consists of fine line segments, is shown at right, find this limit. So let's just kind of logically think through it. If I look at 4, so 1, 2, 3, 4, I'm right here. So looking at that, if I plug into the numerator, I'm going to get 0 because I get 2 minus 2. If I plug into the denominator, I get sine of 4 pi, which is 0. And so I wind up getting 0 over 0. So to do this, I'm going to do the limit as x approaches 4 of my numerator, which is 0, and the limit as x approaches 4 of my denominator, which is 0. And now notice here it didn't say justify, and I'm getting these values from a graph or from an equation. I'm not jumping to conclusions because I am using a continuous function. So you don't need to justify there, but it doesn't hurt to say that. So from there, we know that L'Hopital's applies. So then you would need to take your derivative of the top and derivative of the bottom. And again, these are just a little bit more interesting derivatives. So derivative of the top is 2h prime minus 1/2 x to the negative 1/2 over, okay, derivative of sine is cos, leave the inside alone, times derivative of the inside, which is pi, right? The derivative of pi x is just pi because it's a constant times x. So now I can substitute in there. So this is 2 times the derivative of h at 4, which is just the slope. So this is 2 times 1 minus 1 over 2 square root of 4 all over cosine of 4 pi times pi. And we can simplify down from there. So let's look at what they would expect, or let's actually simplify that down. So this would be 2 minus 1/4 over cosine of 4 pi. That's coterminal. There's 2 pi, there's 4 pi. Coterminal is 0. So cosine there is 1, so that's just pi. And then I'm going to multiply through by 4. So that's 8 minus 1 over 4 pi, which would be 7 over 4 pi. Now, the way that I will grade this and the way the AP would grade this is this. And this will be the last thing for tonight unless you guys have more questions. To get the 1 point for L'Hopital's rule, you have to show the limit of the top and the limit of the bottom separately. And you have to attempt the derivative of the top and the bottom. To get the second point, you need the derivatives. So you need to attempt the derivatives to get the first point. You need the correct derivatives to get the second point. You can get no points if you don't show limits. Even if you do all the right math and have all the right answer, you are not eligible for any points if you don't show limits, right? You're in a calculus class. Show some calculus. So that's the big thing. I would say if you get a limit and it's 0 over 0, then L'Hopital's just says take the derivative of the top and derivative of the bottom and then take the limit of that function. So guys, that summarizes what we've done this unit. So I am going to stick around for 5 or 6 more minutes, see if you guys have any questions. Otherwise, watch this again, pause it, send me questions, whatever you need to do. You have 3 review sheets in your stamp sheet packet. You have 2 con assignments due. You have 2 teachers who are willing to help you in any way we can. So please, please, please ask any questions, get any help you need it before the test. And I will talk to you guys later. But I'll stick around for a couple minutes for questions.